These are the notes for chapter 17, which is about chemical equilibrium. If you didn't pick up the PowerPoint, it's available online. If you have that, it'd be a little easier to see than the background here. So some reactions can go either way. They can either go reactants to products, which is mostly what we've talked about so far, or they can go from product to reactants. And it's kind of like like filling water in a bucket. It doesn't all slant up to one side, doesn't slant to the other side unless it's tilted that way. It eventually goes back and forth until it reaches an equal level that it's happy with. That's how reactions go. And they're not always 50-50. They sometimes can be 99 and 1%. So in other words, almost everything goes to products, but a little bit will go back. That position is called the equilibrium position. And that's kind of the main focus of this chapter is chemical equilibrium. Chemical equilibrium is that point where it finds that balance and it is happy. Say happy, but where it's the physical nature of things is that's where it's going to be at a certain temperature. Temperature does affect it, so temperature can shift equilibrium a little bit, and we'll talk about that a little later. The law of equilibrium says that at a particular temperature, the equilibrium point of a reaction is equal to the product of the product over the product of the reactants. So that's KEQ equals the concentration of the products over the concentration of the reactants. If there's more than one, then we multiply those. And we represent that, you can see on the next page here, we represent that with, here's our general equation form. Here would be the KEQ, and they use K. I use that so that it would remind me to talk to you about. Some books use KC, which is kind of like constant. Some books use K. Most of the better books use KEQ because there are several types of K constants, as we know already. There's KSP. There's you know that there's K used in rate laws. So we like to say KEQ because that's the equilibrium constant. So at the bottom right, there is an equation that you could actually, if you want to try to do this format and write the KEQ expression, the expression isn't something that is solved, it's just like an algebraic expression. Use this format on the left and on the middle and see if you could put together that KEQ. I'm going to write it up on the board here, and hopefully you'll be able to see this. So our KEQ is going to be equal to the product. In this case, there's just one, so we don't have a D because there's just a C. So the product raised to the power of the coefficient, so it's to the second power because it was 2NH3, over the reactants, which are N2 and H2, raised to the power of the coefficients. In this case, hydrogen is to the power of 3. There you go. That's our expression. Now, I may give you, and I definitely will give you, values for this. There's no chart to look up, but I will give you values and ask you to solve for the KEQ. Something important about this is notice that the products are on top and the reactants are on the bottom. Since the products are the numerator, if the products are dominant or bigger, that means that we're going to have a big number over a small, and that's going to be a value greater than 1. If the reactants are dominant or favored, then there will be a bigger number in the bottom, and that's like 1 over 4, that's going to be less than 1, whereas 4 over 1 is going to be greater than 1. So you need to know this because on the quiz, on your review, I'll be asking you, are products favored? Once you've solved for the KEQ, if it's greater than 1, products are favored. If it's less than 1, reactants are favored. If it's equal to, if it's 0, then neither are favored. So there you go. When the products and reactants are present in more than one state, this represents heterogeneous equilibrium. If they're all in the same state, physical state of matter, we call it homogeneous equilibrium, much like the terms we used in the last chapter. It says in the bottom here, do make sure that you can write KEQ expressions and that you can solve for KEQ given the values. So we move on and talk about factors affecting equilibrium. And to do this, I've got a good visual. Matter of fact, this is one of the things I think that makes this not such a hard topic is using the aquarium that I have here. And notice I've got an R, I've got an R on this side, and I've got a P over on this side. This is reactants, that's products. Okay, so I'm going to tilt you out a little bit here, you see the glare of the screen there. But so you'll get the main idea though. So the reactants are the side with the R. The products are the side, and we have a double-sided arrow here. So we know it's a reversible reaction. And you see reactants and products. Okay, if I let that whiteboard be back there, now you can see that a little better. So the whole thing about Le Chatelier's principle is that you have to think in terms of this aquarium. Now, I've got it balanced 50-50, but we could have it like this, and notice it's not in equilibrium, it's jumping around, but once it sits for a while, it will be in equilibrium. In this case, we would have to say reactants are favored because most of the material is on the reactant side, and in this case it's water, but we're using this as an analogy. So you can see that here reactants would be favored, KQ would be less than 1. So, and we could also have products favored. You see how we've upset the system and it jumps around for a while, but eventually it settles out and finds a good equilibrium. So that represents some important things you should know about reactions, that after it sits for a while, it goes into equilibrium. Water's going that way, water's going that way. So it's called a dynamic equilibrium. In a reaction, the products and reactants are moving back and forth, but when one goes that way, one goes that way, and that keeps it in a dynamic equilibrium. Now I actually have a reaction, and kind of hard for you to see down here on the bottom. I'll see if I can go over it in red. So we've got N2 gas, and we've got 3 H2 gas, and we've got 2 NH3 gas, and I put heat over here on the other side just so we had it marked, and HEAT, so you can see that a little better. So this is going to represent some of the things we need to talk about. Now, the whole idea of Le Chatelier's principle can be that when we scoop out, which we're scooping on the product side, what does the water do? Well, when we take away, the water fills behind where we left a hole. When we add, if we add the product side, the water hits and goes that way. It doesn't pile up over on the side where we add it. It always reacts by shifting away from where we add it or to where we scoop it. And that's the whole concept that you need to be thinking about for all of these. So let's talk about, what if we take away from reactants? Well, if we take away reactants, it fills and shifts towards reactants. That would be your answer if I said, if we take away reactants, how does the system respond? It shifts towards or makes more reactants. If I add reactants, then it's going to shift and make more products. Adding, shift away. Take away, shift to, fill the hole. So let's talk about the heat. Okay, so over here I have heat on the product side. It is an exothermic reaction, heat's being released. So if I treat heat just like another product, then you already know how to do it. So if I take heat away, in other words, I cool the whole system. If I take heat away, well, the reaction is going to shift to fill. What if I heat the reaction and add heat? See, I can't add heat on the left or the right. I have to add it to the whole thing, but it only adds where heat is present in the equation. So if I add heat, it shifts to the reactants. It's going to shift away from where the heat is. Obviously, if the heat was on the other side as a reactant, then it would do the reverse of what we just said. What about adding pressure? Well, the way to do pressure is to count the number of moles of gas. So over here, I've got 1 N and 3 moles of H. So I've got 4 moles over here. I only have 2 moles of gas over here. this side has the most moles of gas. So when I add pressure, this side is going to be affected more. So adding pressure is like dumping in material here, because the pressure is being added mostly to the side where there's most moles of gas. So adding pressure would shift to the least amount of moles. Taking away pressure shifts to fill. It would go to the side where the most moles of gas if I took pressure off this whole system. Remember, I can't pick one side or the other on the reaction. It's all in the same container. So think about Le Chatillier's principle and this aquarium, and that will help you. There's one other thing that they mentioned. They talk about increasing volume. Well, you know, we've got an answer for that too. There's an easy way to, if you remember, we use this when we increase the volume, we decrease the pressure. So just think about it in terms of pressure. Increasing volume would decrease pressure, and you already know how that acts. Decreasing volume would be increasing pressure because we're mashing the molecules together. So there you go. You've got the four main ideas of how Le Chatillier's principle works. Hopefully that will help you in learning Le Chatillier's principle. Okay, so, and we'll get this out of the way. So, let's see. All right, so we move on, and that's kind of taking you through this this whole set of ideas here for Le Chatillier's principle. So next we'll talk about KSP. So we've already talked about the KEQ, and the next main concept that we have, the third main concept, KEQ, Le Chatillier's principle, and KSP. This is the third main topic. KSP is the product of the products. So how do we remember all these things that we've had? Well, back in chapter 16, we had rate laws. Think of R as in reactants and rate law. R and R, like rest and relaxation. We all like that. R and R is rate law is reactants. KEQ, think equal. We have products and reactants, equal rights for both. For KSP, think of product of the products because it's solubility product. It has the word product in it. So that's how we keep track of all three of these. And what we have to do, first step, write the ionic compound and then show how it splits into pieces. Draw a line after the first element, and that's how it breaks apart. Only exception to that is when you have ammonium NH4. NH4 is a polyatomic ion, and it's positive. It's the only one that we deal with that's positive. So if you see NH4, draw a line after the NH4. But that splits it into two parts. Not going to have 3 or 4 or 5 parts. Don't break the polyatomic ions up. You have a polyatomic ion chart, look at it, or you're familiar with it. That way you'll know how we break it into 2 parts. So we have the 2 parts it breaks into, and then we simply write KSP equals, and then 2 sets of brackets, KSP equals 2 sets of brackets because we're going to have 2 pieces. And on this example, we've got PB2 plus. How did we know it was PB2 plus? Because this 2 came from the positive ion. The 1 here came from the negative. So Cl is a 1 minus, and Pb is a 2 plus. Also, review over the chart. You know how to identify charges based upon periodic table. If it's Roman numeral 1, 2, or 3, it's plus 1 or 2 or 3. If it starts like over at fluorine, chlorine, bromine, the 7A, remember that the noble gases are all 0 ions. The next column to the left is all minus 1s. The next over above the stair steps, minus 2. The next over all, minus 3. That identifies most of the ions you'll be dealing with here. So for the solubility calculations, there's a chart on page 615, and this will be given to you and you're possibly useful. It is the KSP at 25 degrees Celsius or 298 Kelvin. And when you do these problems, in almost every case, you're going to be looking up the KSP for the substance you write the KSP expression for. Okay, now this one's a little more complicated because Cl has a 2 on it, which means there are going to be 2 parts when it splits. That 2 is going to be the power because there's 2 CLs. There's 2 CL minuses when it breaks apart. And if you have trouble identifying that, come in for a little extra help. But this one's actually a little bit more complicated because PB, there's 1, that goes to the power. This 2 is going to go to the power there. And we have PB2 plus times CL1 minus to the second power. Okay? And then we do, basically, if you look this up, then we're able to do some calculations and solve for those. So we're going to move on, and we're going to do a basic KSP. So I'm going to start out with something simple, like we'll do AgCl. Okay, so AgCl breaks into Ag plus Cl minus. 2 parts. KSP is Ag plus times the Cl minus. Remember, the brackets means molarity. It also, besides being a separator and a like parentheses, and to tell us there's an operation of multiplication here, it means moles per liter or molarity. Okay, so how do we solve for this? Well, this is where we talk about the pin and cap concept. So the AgCl breaks into 2 parts, and when it breaks into 2 parts, it's like this pin and cap. There's 1 pin and 1 cap. When it breaks into 2 parts, we got 1 Ag and 1 Cl. That's how you know that they're going to be equal. The Ag concentration is going to be equal to the Cl. And so by laws of equality and substitution, we know that if we were going to solve for the Ag, now all we got to do is say, well, if Ag equals Cl, then Ag can be substituted for Cl. Well, now it's easy. We had 2 unknowns. Now we got 1 unknown. The KSP, we go look at the chart, and it's on your possibly useful. We look up AgCl, it's 1.8 times 10 to the negative 10th. Yep, 1.8. So 1.8 times 10 to the negative 10th, molarity squared is the unit, equals x squared. Why do I call it x squared? It's just easier for some people to do that. Ag is equal to x. Cl is equal to x. If you want, you could do Ag squared. But, it doesn't matter. We just see we got Ag times Ag. I'm going to represent Ag as x. So if we have x squared, we need to know what Ag is, or x. Square root of that gives us x, which also equals Ag. So that's it. It's just a matter of look up the KSP. If these are equal, then make your substitution. We have Ag squared or x squared, depending on what you want to use. It's a variable. It's whatever you want to use. So we do the square root of the KSP and the square root of that. Now we know what one of them equals. And when you do the square root of that, so just to make sure if you're doing this calculation on your own, 1.8, and then you hit the EXP or the EE key, and we're going to hit 10 and the plus minus. Remember, if you have an 83 or 84, TI 84, you got to hit the sign, then the number. But on these calculators, you hit the number, then the sign. And we hit equal, make sure you got that registered, and then you do the square root, and it's 1.3416 times 10 to the negative 5th. We've got 2 significant digits. So the silver ion concentration would be 1.3 times 10 to the negative 5th molarity. That's the concentration for silver. That's how you do the KSP problems. Now, the other problems, the one like we talked about with the squared, a little bit more complicated algebraically, but it's not any more complicated than what we had. Let's write that one up with PbCl2 again, and I'll go through that. I recommend that if you weren't here in class that you come in and get this, because it's a little bit more to it. But we had PbCl2, and that corresponds to a KSP of Pb2 plus times Cl minus squared. Okay, now what's different here is when this breaks up, we've got 2 Cl minuses and 1 Pb2 minus. So it's not the pin and cap. It's actually the pin and 2 caps. Okay? So when we have 1 Pb, how many Cl's are there? 1, 2. 2 caps. So we're going to use X this time because it really gets confusing if you don't use X. So we're going to say that since Pb is 1, that's going to be represented by X. And since for every one of these there's 2 Cl's, we're going to say the Cl is 2X. So I'm going to go in here and say 2X instead of Cl. And I'm going to say 1X instead of Pb. Now we just got one unknown. We look up the KSP, which we know we can find. And for PbCl2, it's 1.7 times 10 to the 5th. So 1.7 times 10 to the 5th equals x times 2x squared. Well, this is where you got to really be careful. What's 2x times 2x? Well, 2 times 2 is 4, and x times x is x squared. So that is 4x squared times another x. We end up with 4x cubed. So we have the KSP equals 4x cubed. It's just algebra now, and we've simplified the chemistry part of it and most of the algebra. So we divide both sides by 4 and then take the cube root of both sides, and that gives us cube root of x cubed is x. So what is this value? Well, you enter it this way. You're going to enter the 1.7, and then the exponent of negative 5. Okay, it's 1.7 times 10 to the negative 5th. Divide by 4. Make sure you hit equal. And then you do the shift plus minus on this calculator. And we get 0.01619, which is 0.2 significant digits. That will be 0.016. Molarity is equal to X. X is the lead. That is the Pb, or lead, concentration. We already said chlorine is twice as much because it's 2Cl. So that would be 0.032, which is twice as much of the molarity as 1x. It's 2x. So you get 0.016 molar for lead, Pb2 plus, and 0.032 for the chlorine. Work through this one. If you don't get that, come in for help. And there's lots of extra practice on the foldables. You should work on those. So we finish up. We've got 2 more types of problems, and they're both KSP. So they're not that difficult. Next one is the precipitate, and it's a KSP problem. So what are we going to see on this? Well, first of all, it will say, will a precipitate happen if you mix, and it gives you 2 solutions. And it usually will say, will a precipitate of, let's say, AgCl happen? Okay? And that's not showing up real good. I think the red will be a little better. So will a precipitate of AgCl happen? So that tells us that's what we make our KSP on. And we already did a KSP for AgCl. It splits into 1 Ag plus 1 Cl minus. Pretty simple one. So we end up with Ag times Cl equal to KSP. Okay, that's our KSP expression. Now, we're trying to find out, will a precipitate happen? We don't know that this is saturated, so we can't really call it a KSP. We have a special term, we call it a QSP. The QSP is kind of a question about, well, I'm going to take these solutions you tell me I have, and I'm going to multiply this, and then I'm going to see, is it bigger than the KSP? So here are 2 solutions. I'm going to say we have 0.0020 molar NaCl, okay, and you say, well, wait a minute, where's this Na stuff? Well, you're right. The Na is not part of this, but the Cl is. The Na is what we call a spectator. It's a vehicle that brings the Cl ion in. We can't just dump chlorine in because chlorine's a gas and it's a very toxic gas. NaCl is safe, and when we put it in water, it splits, and the Na really splits. It goes away, and it doesn't affect anything. The Cl, we want to know what it is. Well, we've got 0.0020 molar, 0.0020 molar Cl, and we just ignore this. Kind of like front wheels of the bike. Somebody asks you, how many front wheels do we need to replace? Well, I've got 2 bikes. That means 2 front wheels, okay? Don't worry about the back wheels, those you bought last week. So, we plug that in. Now, we look at what's the other solution. Well, I'll tell you that we had a 0.001 molar AgNO3, and you say, well, NO3, yeah, that is a spectator too, but the Ag is what I need, and it's 0.001. 0.001 is the molarity for Ag. Then we're pretty much done. We multiply these two, and we get this QSP. And then that value you get, which is 1 times 2, let's see, we got 1, 2, 3, 4, 5, 6. So it's like 2.0 times 10 to the negative 6 molarity squared. That's our QSP. Well, you're going to go look at the KSP, and if the QSP is bigger, then we have a precipitate. Think about like a container. If you had a gallon container, you try to put 2 gallons in it, it's not going to fit. It's going to overflow. The QSP is bigger. Now, don't get confused. This is 10 to the negative 6, and for AgCl, I think the power is 10 to the negative 10th for the KSP. So you might say, well, wait a minute, 10's bigger than 6, but it's negative 10th. This negative 6 is 0.00002. 5 zeros and a 2. Whereas the KSP is 9 zeros. It's a lot smaller. So we're trying to fit in more than can be held by the solution. And there's some example problems on your practice. Please work those. And we'll look at one more type of problem. And the other type is called the common ion problem. And where we have a common ion effect, there are 2 solutions. Now, you might say, well, darn, we just talked about 2 solutions. Now I'm getting them all mixed up. Well, the one that the 2 KSPs, they have 2 solutions. One of them is precipitate. And for my questions, they will always say, will it precipitate happen? Boom, precipitate problem. If you have 2 solutions and it doesn't have that will it precipitate happen, common ion problem. So here's how you do that. First step is you look through and find what you're going to write the KSP for. And in most cases, you'll be writing the KSP for the saturated solution. It will say you have a saturated solution of, and so let's use AgCl again. So we have a saturated solution of AgCl, and what we need to find out, the final answer here is going to be what's the concentration, the final concentration of the Cl once we add both solutions. Okay? First solution, concentrated AgCl. So you say, well, I know that for AgCl that it's 1.8 times 10 to the negative 8, 1.8 times 10 to the negative 10th molarity squared. And remember how we solved for that? Ag times Cl, but they're equal, so we did Ag squared. So Ag squared, square root of that, and we find out that the square root of 1.8 and then exp to the 10th negative, and then shift square root, is 1.3 times 10 to the negative 5th. So that's 0.000, let's see, 1, 2, 3, 4, 1, 3 molar. That's our first source of silver. But we have 2. Remember, it's common ion. To this, we're going to add let's use this solution up here. So let's say we still had some of this left from the last problem. We're going to add 0.001 molar silver nitrate. So here's our next one, 0.0010 molar silver nitrate. Remember, the nitrate's just a spectator, so it goes away. So we don't have to worry about that. And so now we've got our two sources of silver. Well, here's the thing. You can look ahead, and most of y'all are smart. You're going to see, well, wait a minute. This is 10 to the negative 10th. When I do the square root of 10 to the negative 10th, it's going to be half that, which is 10 to the negative 5th, and that's what it turned out to be. When we do significant digits, this first source of silver drops off the map. It doesn't even show up. And for most of your problems in pre-AP and first-year chemistry, that first source is going to drop off the map. So if you're feeling lucky, or if you really are good, you look at this and say, let's see, 4 zeros. Yeah, that's not a factor. Here's what you do. You write the KSP. KSP equals AG plus times CL minus. We're solving for the CL minus. We know the KSP for this is 1.8 times 10 to the negative 10th molarity squared. So all we need is to plug the AG in and solve for the CL. Well, now we know that first source. Don't even worry about it. Look at it. You see that it's not a factor. What is our amount of silver? It's only the second source, which is 0.0010. We divide both sides by 0.0010. 0.0010, and the 1.8 times 10 to the negative 10th divided by 0.0010, which was our second silver solution. We divide and we get our answer. We get the amount of chlorine. So I'll run that real quick in case you're solving it. You could rewind this if you need to. So we have 1.8 exp to the 10th, negative 10th, divided by 0.001, and we get 1.8 times 10 to the negative 7th. That's the answer to what's our chlorine concentration. Now remember, it's like an auditorium. You have 500 seats. If you got 500 people, nobody else can fit. But the chlorine and the silver are all trying to sit, and if you put extra silver in, you're going to run out some of the chlorine seats. Okay, so the more stuff you put in there of silver, the less chlorine you're going to have. Because remember, we're multiplying the silver times the chlorine. When you multiply the silver times the chlorine, they both count equally. So if we have a bunch more silver, we have two solutions, then less silver. Or I'm sorry, less chlorine. Because there's more silver. It's like a seesaw. One of them goes up, the other's got to go down. So that's chapter 17 in a nutshell, pretty big nutshell, but you need to rewind any of this, do it. If you need to look at the foldables, I have foldable A and foldable B for chapter 17, www.landerson.net. Go to pre-AP chemistry, chapter home pages, and then 17, and you'll get some extra practice. Work on your review. Good luck and do a good job.